Hello students. Today we are going to talk about a critical area of software engineering, which is software reliability and quality management. You can think of software quality as a overall health of the product, and reliability is a vital sign, a core part of that health. We will start with the fundamental concept of reliability, then move to a powerful testing technique, and finally, we will zoom out to understand the broader framework of quality management and how an organization can systematically improve itself. We'll move on to the next slide. What is software reliability? I want you to think about this question. When you use an app on your phone, what makes you trust it? What makes you so confident that it will work correctly every time you open it? Just think about it. That's the core of the software reliability. Let's break down the formal definition. Software reliability is the probability of a failure-free operation of a software system for a specified period of time in a specified environment. Let's unpack that sentence piece by piece. First, we have probability. This tells that reliability is not a yes or no question. It is a measure. It is a number between 0 and 1 or a percentage. It's the likelihood that something will happen. In this case, the likelihood that the software will work as expected. We can never say software is 100% reliable, but we can aim for a very high probability. Next, failure-free operation. This is simple enough, right? It means the software does what it's supposed to do without crashing, without producing the wrong output, and without any glitches. A failure is a deviation from the expected behavior. This is triggered by a fault in the code, which is flaw or a bug. So, failure-free operation means the user doesn't encounter any of these unexpected faulty behaviors. Then we have for a specified period of time. Reliability isn't a static concept. It is tied to time. A system might be reliable for 5 minutes, but not for 5 hours. A web server might be reliable for 99.99% of the year, but not for 100%. This is why we use metrics like mean time between failures, that is MTBF, which is the average time of the system works without failure. Finally, we have in a specified environment. This is the critical part of the definition. Software behavior can change dramatically depending on where it's running. Think about an app. It will run differently on an Android phone versus an iPhone, or on a phone with unstable internet connection versus a stable one. The environment includes the hardware, the operating system, the network conditions, and even the way the user interacts with the system. We can't talk about reliability in a vacuum. We have to specify the conditions under which the software is being used. So in short, software reliability is a quantifiable measure of how dependable a piece of software is under a specific set of conditions over a specific period. It's the difference between software you can trust to work and the software that leaves you guessing. Let's move on to the next slide. Before we dive deeper into software reliability, we need to master two of its most fundamental concepts, which is faults and failures. They are often used interchangeably, but in software engineering, they have very distinct meanings. I want you to think of them as a cause and its effect. Fault is the cause. It's a defect or a mistake in the code. Think of it as a potential problem waiting to happen. It's something you, as a developer, accidentally introduced during the design or coding phase. An example might be simple typo in a variable name, an incorrect mathematical formula, or a logical error in an if-else statement. This fault is just sitting there dormant in the code. A failure is the effect. It is the observable undesirable result that happens when a fault is triggered or executed. A failure is what the user sees. It is the program crashing, the data being corrupted, the wrong output being displayed, or the system freezing. The failure only occurs when the conditions are just right for the hidden fault to become an active problem. Let's use a simple analogy: baking a cake. Imagine your recipe calls for 2 cups of flour, but you accidentally wrote down 2 tablespoons instead. That typo, the incorrect quantity of a flour, is the fault. It's the mistake in the instructions. Now, you hand this recipe to your friend. When they try to bake the cake, they follow the instructions exactly. They add only 2 tablespoons of flour. The moment they take the cake out of the oven, they find it's hard, inedible mess. The inedible cake is the failure. It's the observable incorrect result of the following the faulty recipe. The fault existed the moment you wrote the recipe, but the failure didn't happen until someone actually used the faulty recipe to bake the cake. I hope you understand the concept. Let's apply this to a real world using the simple example of a self-driving car navigation software. The fault will be a developer makes a small coding error that causes the car's object recognition system to misclassify the traffic cone. This misclassification is the fault. It's the latent defect in the code. The failure would be the car is driving down the road. It encounters a traffic cone. The faulty code is triggered and the car's system incorrectly identifies the cone as a non-threatening object, like a piece of paper. As a result, the car swerves dangerously to avoid it or even hits it. That dangerous collision is the failure, the tangible negative outcome that the user experiences. The fault was there from the beginning, but the failure didn't occur until the car encountered that specific situation on the code. Understanding this distinction is the first step towards building more reliable software. Our goal isn't just to fix failures, it is to find and eliminate the underlying faults so that failures never have a chance to occur in the first place. Move on to the next slide. Now that we understand the difference between a fault and a failure, let's talk about how we actually measure reliability. It's not enough to just say software is reliable. We need to quantify it. We use special metrics to put a number on a reliability, making it tangible and measurable. One of the most common metrics is mean time to failure, or MTTF. This is the average time that a system operates without a failure. Think of it as the average lifespan of a system between 2 failures. The higher the MTTF, the more reliable the system is. Let's go back to our self-driving car. For a company building this car, they wouldn't just say our software is safe. They would set a specific measurable goal for its MTTF. They might aim for an MTTF of 1,000,000 hours. That means on average, they expect the software to run for over 114 years before it encounters a critical failure. This high number is a direct and concrete measure of the company's commitment to safety and reliability. Now, not all software is like self-driving car. For online services like a company that provides cloud computing, their reliability is often measured a little differently. They focus on availability. Availability is a measure of how often a system is operational and accessible to users. This is what we often hear referred to as the number of nines. For example, a service that has 5 nines of availability, 99.999%, is extremely reliable. It sounds close to perfect, but what does that number actually mean? Let's do a math. A year has 5,25,600 minutes. If a service is available 99.9999% of that time, that means it's only down for 0.001% of the year. When you do that calculation, you get less than 6 minutes of downtime per year. As a consumer, you might not notice a few minutes of downtime, but for the business that relies on that service, it could be the difference between making millions of dollars in sales or losing them. So, for software reliability, we don't just talk in vague terms. We use metrics like MTTF to measure how long a system can run without failing, and availability to measure how often a system is working. These metrics provide a clear, objective way to define and compare the reliability of different systems. Let's move on to next slide. So far, we have defined what reliability is and how to measure it. Now the question is, how do we test for it? You are all familiar with traditional software testing. We create test cases to find bugs. We try to break the system. We are looking for hidden faults so we can fix them. But testing for reliability is different. Our goal isn't just to find every single bug. Our goal is to estimate the software's reliability in its actual operating environment. We want to answer the question, will the software work reliably when a real user is using it? To do this, we use a technique called statistical testing. This method is based on a crucial concept, the operational profile. An operational profile is a quantitative description of how the software will be used in the real world. It's a list of all the different functions of the software can perform along with the probability of each one being used. Let me give you an example. Imagine we are building an e-commerce website. This website has many functions: searching for a product, viewing a product page, adding an item to the cart, checking out, writing a product review. Now in the real world, not all these functions are used equally. Most people who visit the site probably search for products and view products pages. Only a small percentage will actually go through the checkout process, and even a fewer will write a review. Our operational profile would reflect this. It might say, searching for a product will be 50% of the time. Viewing a product page will be 30% of time. Adding an item to the cart will be 15% of the time. Checking out will be only 4% of the time. Writing a product review will be only 1% of the time. The total of these percentage adds up to 100%. Why is it so important? Because it helps us focus on our testing efforts. Instead of randomly testing every function equally, we can write our test cases to mirror the real world usage. This means we will run a lot more tests on search and view product functions and fewer on the review functions. By doing this, we are not just trying to find bugs. We are collecting data on how often failures occur during the typical real world usage. This allows us to make a statistically sound estimate of the software's reliability before we release it. This results of this testing directly feed into our MTTF and availability metrics. So in short, an operational profile helps us simulate real world usage during our testing, which allows us to get a realistic measure of our software's reliability. We'll move on to the next slide.